Good day and welcome back to class. We are glad to see you today again and we are glad to have you online. Thanks for coming around again, and we hope that the knowledge which you see the Lord will release unto you. Amen. Now let's quickly take volume or area and volume of expansivity. We've talked about linear expansivity, and now let's quickly see the area and volume of expansivity. Now, without wasting much of our time, we said when solid is heated, the length will increase. And so, once the length increase, the height will increase. And once the height increase, automatically the volume is expected to increase. If there is increase in height and there is increase in length, there is increase in breadth, then there should be increase in the area and in the volume. And so that is why we said, since there is increment in all this, automatically the volume and the area will increase. So let's see how to calculate increase in the area and volume of solid of expansivity after it has been expanded. Okay, so when a solid is heated, it expands in all directions, that is, in length, in breadth, and in height. Hence, there is an increase in the area as well as the volume of the solid. So this is what I just explained earlier, that when a solid substance is heated, the length will increase, then the breadth will increase. So if the breadth increase, the length increase, automatically the area and the volume of the solid will equally increase. So now, we said by definition now, the area or superficial expansivity of a solid is the volume in the area per degree Kelvin increase in temperature. So what do we say now? We said by definition the area or superficial expansivity, that is beta, of a solid is the increase in the area per unit area per degree in Kelvin, per degree Kelvin increase in temperature. So what are we saying is that when we talk of the area of expansivity, we are talking of the what? We are talking of the increase in the area over increase in the temperature. So that is what we mean by that. So when we say area of expansivity, we are saying that the increase in the area divided by the increase in the temperature in Kelvin. That is just what we are trying to say. Alright, let's quickly see. Similarly, the volume or cubic of a substance, this term, is the increase in volume of a substance per unit volume per Kelvin rise in temperature or fractional increase in volume per Kelvin. What are we saying by that? Is that, as we said for area, change in area over change in temperature, that's for area. Then for volume, is going to be change in volume over change in temperature. Change in volume over change in temperature. Now for the area of expansivity, this is what we use to denote it better. Is change in area of our original change times temperature rise. Now I want us to see why we choose to come this way. When we say this is this, of course this is a2 minus a1, then a1 times theta. So we try to divide. So a1 is the area of the temperature of theta 1, then a2 is the area of temperature of theta 2, then theta is what? Theta 2 minus theta 1. Now when you have all this, now let's bring out A1 and A2. Let's see the formula for A1 and A2. We said beta equal to A2 minus A1 over A1 theta. So let's find A1, A2. So by cross multiplication, we know this is over 1. So we have A2 minus A1 will equal to beta A1 theta. Then collect the line, make A subject of formula. So you have A2, make A2 subject of formula. You have A2 will give us what? Beta A1 theta plus A1. So A2 now will give us A1 is common. Write it out, factorization. Then when you use A1 to divide everything here, you have beta theta plus A1 divided by A1, that's 1. So this A2. Now if you want to do for A1, that will be cross multiply. For A1 now you have cross multiply. Beta A1 theta will give us A2 minus A1. We are looking for A1. There is A1 here. So let A1 there is here come to this other side. Let the A1 here come to this other side. We have beta A1 theta plus A1 equal to A2. So factorize as we did here. A1 is common. A1 is common. There you have beta theta plus 1 equal to A2. Then we divide both sides by A1, beta theta plus A1. So you have beta theta plus 1. Beta theta plus 1. So this one can cancel this one. So now our A1 now will equal to A2 divided by beta theta plus 1. Alright. So let's quickly take example on that. Before we go to the example, let's quickly see the formula for volume. Don't forget we said this is the symbol for volume or cubic expansivity. So we said it's equal to change in volume over original value times temperature rise. So this is it. Change V2 minus V1, then V1 times Q. We have this. So to get V2, as we did the other time, let's see our formula for V2. Of course, we know by cross multiplication, this will multiply this. So you have V2 minus V1 equal to V1 theta. So V2 minus V1. So let's make V2 solve your formula because that's what we want to do before. So our V2 will be cubic expansivity V1 theta 1. V1 is crossing V1. So let's find the LCM. As LCM, what's common? V1 is common, so we are factorizing. So we mean cubic expansivity, then temperature 1 plus this one will remain 1. So in short, our V2 now will be what? Theta 1 plus 1. So this is it. V1. Okay. Then for V1, we have it to be what? From here, we say V2 minus Vy equal to this theta. Then we are making V1 such a formula. This will cross. Then minus volume 2. Oh, sorry. This one has V1, so V1, let V1 cross. V2 will be this V1 theta plus V1. So collect this one, factorize. V1 is common. There you have V, this one remains theta plus 1. Then of course you know you divide both side by what? This one. This can cancel this. There you have this to be over. That's why. So our V1 now will be what? V1 will be this V2 over this theta plus 1. So that's V2. Alright. So now, having understood that, let's quickly take this example before we call it a day. A linear expansivity of material is cubic this. So this is the alpha. Then Kelvin raised to power minus 1. So if the length of each side, the length of each side is 10. Find the area of each face and the volume when the temperature is this. Okay. What's the area of a cube? Area is what? L square. That's 10 square, which is 100. Then cube. The volume is L cube, which is 10 cube, 1000 centimeter cube, centimeter square. Let's quickly solve this by slotting our figures into the formula. We said A2 equal to A1 into beta theta plus 1. A1 is 100. Beta, let's use this type of bracket. Beta is 12 times 10 to the power minus 6 times theta. Oh, look at what's the beta. 2 alpha times 2 times theta plus 1. I hope you understand what we are doing. Beta, we have been given beta to be what? This. So put beta, and we are told that alpha is this, and we are told that beta is 2 alpha. This alpha. We are told that beta is 2 alpha. So this one now is 2 times alpha. This one is this, then this is it. Alright, let's expand the bracket one by one and see. 100 into, this is 0.00000012345 times 2 times 30 plus 1. So that will be 100 into 0.12345 2 and 4 times 30 plus 1. So that will be 100. This times 30, that will give us 0, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, 2, 4 times 3 times 10 plus 1. So that gives us 100 into this times 3, this times this, you have 12, to keep 1, this times this, 6 plus 1, 7, then 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, okay, times 10 plus 1, that will give us 100 into times 10. Of course, we know the 0 will reduce by 1, times 10, the 0 will reduce by 1, 0 will reduce by 1, so you have 0.12345 7, 0.1234 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 7, 2 plus 1. So our answer now will be what? 100 into 1.123472. So when you multiply, you have 100.0072. That is the area 1. Area 2, sorry. Alright. Now let's do the second one, which is the volume. They said, and the volume. Of course, we have gotten the V1. This is our V1, 1000. So V2, equal to this is it. So we are taking this tau, and that's what, 3 alpha, 3 times, what's our alpha? Alpha is what? 0.00000012. This one is times 3. Okay, so we've done this, plus, okay, times theta, 30 plus 1. This is, I hope you understand this. Oh, this tau is giving us 3 alpha. And we are told that our alpha is this, so multiply by this, multiply by this, and add by this, to this. Alright, let's quickly see. V2 now is going to give us 1000 into 3 times this, that's what? 3, this is 12, that's 6. 3 times 2, that's 6. 3 times 1, 3. Then 3 times the remaining 0 is 0. 0.12345. So we now have times 30 plus 1. Okay, V2 now will be 1000 into, let's multiply this as we did the other one, 0.0000000 3 6 times 3 times 10 plus 1. So V2 now will give us 1000 into 3 times 6, 18, 8, keep 1, 3 times 3, 9, plus 1, 10, 5, 0, keep 1, 10, 3 times this, 0, add 1. So we have how many zeros? 1, 2, 3, 4. 0.1234. Good. Times 10 plus 1. So V2 now will be 1000 multiplied by 10 is moving 1. So that will be 0.123108 plus 1. So V2 now will be, I think you understand these things that I'm doing. We use this to multiply this. Of course, the point will shift once. So if we shift once, remaining 3 zeros, 1.3 zeros, 1.3 zeros, then this one. So that's it. So when you add, you have 1000 into 1.000108. So V2 now is going to be multiply this by this. 1, 2, 3. 1000.108 centimeter cube. So this is the answer for this volume. Why? This is the answer for the second area. I hope you understand everything we've done so far. So far so good. We've been able to see how to calculate the area and volume of expansivity. We've also been able to see linear expansivity. Thank you very much. See you in the next video. God bless you.